It's no secret that STEM disciplines have high drop rates, but why is that? It's a tough question to answer. Sure, we could look at demographics like test scores or course grade, but this is not the whole picture. We can glean additional information from looking at connections and relationships between things like students and other students, their teachers, or even their test responses. One way to look at how these things are connected is to use network analysis. Network analysis is a method used to investigate relationships between things. It can be incredibly useful to researchers in many fields, but I want to talk today about a couple of applications in education research. In order to talk about network analysis, we first need to talk a little bit about what a network is. A network is comprised of two parts: the objects, usually called nodes or actors, and the connections between them, usually called edges or links. Let's understand this by looking at an illustrative example. I want you to imagine that you're going on vacation and you need to fly to your destination. You want to find a way to get from your local airport to your destination. In this example, we can think of the airports as being the nodes and the flights between them as being the edges. If you live in a large city, there are likely lots of flights to and from your airport, so the node has lots of connected edges. If, on the other hand, you live in a smaller town, there are probably fewer flights. In some cases, there's probably no nonstop flights between the two airports, so you must take a connecting flight, but you will be able to make it to your destination in the network. There's one other network characteristic that I need to bring up, and that is the concept of centrality, which is the measure of how in the middle a node is. There are different ways to measure centrality, but I only want to mention one: closeness. A node that is high in closeness centrality is independent and does not need to rely on other nodes in order to access the full network. To go back to our airport example, these central nodes can be thought of as being large hubs, like Denver or Atlanta. Now that I've talked a little bit about what's going on, let's look at a couple of applications of networks in physics education research. The first paper I want to talk about is by Zwolak et al., which looks at student integration in introductory Physics 1 classrooms and the impact on Physics 2 enrollment. The authors collected data from the students about which of their peers they had meaningful interactions with. They then translated this data into a network of students connected by their interactions, much like the airports and flights in our earlier example. Quote, "Students with high closeness scores have easy access to information from many sources. They are also, by sheer nature of this measure, connected to many students and might experience better social and emotional support. These students were more likely to persist and enroll in introductory Physics 2. There's another example that I'd like to talk about a bit, and it comes from Brew et al. In a 2016 paper, where the authors develop a new way to use this network analysis to look at the responses students gave on a multiple choice test. In this case, the nodes in the network are the answers that students chose, and an edge is put between any two answers that a single student selected. The more students that picked those two answers, the more important the edge. By examining networks like this, we can see interesting patterns. For instance, we can see what kinds of mistakes are the most strongly connected. If these mistakes follow some similar pattern, we might be able to identify areas to improve instruction techniques. For instance, in the Newtonian model of physics, the second law, F equals ma, tells us that a force is required to change either the direction or speed of motion. In the example of a tennis racket hitting a ball, the force from the racket on the ball only exists while the racket and the ball are in contact. In the impetus model, this force exists after the ball has left the racket, as a sort of fuel that may deplete over time. This is a common misconception in students, and it was the peak of physics theories in the 6th century, so it's a reasonable mistake for students to make. The authors of this paper identified a group of nodes that is largely comprised of answers that follow this exact theory, and thus dubbed it the impetus module. While I've only discussed applications in physics education research, the methods I have talked about could easily be used to research other disciplines. In any field, the goal of this analysis is to reveal information that otherwise would be buried. Now it's up to you to take that information and use it to improve the world.